Now looking at a lateral surface to find the other motor areas. So this specimen is from our brain laboratory. You can see here the middle cerebral artery peeking out from within the sylvian fissure to supply the operculum. That's our primary motor cortex outlined for you. And that is this part here is the knob corresponding to the motor hand area. And this is our face area. So a majority of the lateral surface of the precentral gyrus is actually dedicated to the face. So the principle here is one neuron in the precentral gyrus to one muscle. So the more neurons, the more skillful or more dexterous that motor function is. So for the hands, here by the thumb and the index and the little finger have a lot of neurons dedicated for this, and a lot of neurons dedicated for the face, for the facial expression. And further down here, near the banks of the sylvian fissure, is the mouth and tongue area. So the more dexterous the part of the body is, the more neurons allocated for that part of the body. Then surprisingly over here is the eye area, the frontal eye area, or the frontal eye field. This is the intersection of the precentral sulcus and the superior frontal sulcus. So taking that motor strip and isolating here on this slide. So we show here the leg area, the arm area, the face area, and the tongue area. So to get from point A to point B, they need to traverse several obstacles. So these are the different obstacles: the lateral ventricle, the caudate nucleus, the putamen, the globus pallidus, and the thalamus. So not all of the primary motor cortex fibers need to traverse all these. Only the leg fibers will need to encounter the lateral ventricle. So here on a coronal cut, you see here the fibers or the axons of the neurons here for the leg and foot area traversing vertically in the centrum semivale, in the corona radiata, until they encounter the lateral ventricle over here. The lateral ventricle and the caudate nucleus. So in a normal brain, not too much impact, but if you have a ballooning of this lateral ventricle, when you have hydrocephalus, it can stretch the leg fibers passing through here on its way to the internal capsule. Here, the hand area, the neurons and their axons do not encounter much interference from the lateral ventricles. They descend here in the centrum semivale, corona radiata, into the internal capsule over here. Seen here, the continuation of the internal capsule with the cerebral peduncles crus cerebri. As to the face area, again, no interference here. The face area axons of the neurons here will move down here in the corona radiata into the internal capsule. And here, the widely allocated neurons of the tongue and mouth will send their axons as well into the internal capsule. So here, demonstrating for you the obstacle course for the leg fibers on their way to the anterior limb of the posterior limb of the internal capsule here, between the putamen, globus pallidus, and the thalamus here. Okay, so superimposing this now on a axially cut brain specimen. This is the anterior limb, this is the posterior limb of the internal capsule. Right? So you see here the internal capsule, which closely resembles the cerebral peduncles here. Just showing you what happens as the fibers approach the internal capsule. There will be some twisting involved. some reorientation, wherein the fibers for the legs will now end up in the most posterior portion of the posterior limb of the internal capsule. Whereas the fibers for the hand area will also twist and come to be located more anteriorly to the leg fibers here in the posterior limb of the internal capsule. And the most anterior would be the fibers coming from the face and the tongue. Now, these are the slices from the Big Brain Project, just demonstrating to you that cut where the diencephalon leads to the midbrain, where the internal capsule becomes your cerebral peduncle's crus cerebri. Alright, so here now, comparing a supratentorial cerebral hemisphere slice with a slice of the midbrain, where the internal capsule is analogous to the crus cerebri of the cerebral peduncle of the midbrain. The orientation of the fibers are preserved. The arm fibers are anterior to the leg fibers, and together these are your corticospinal tract fibers. And they are lost in the sea of non-corticospinal tract fibers because 1 million only out of the 20 million fibers found here are corticospinal tract. The rest are connections from the frontal lobe to the pons. Now, using diffusion tensor tractography technology, we need to know our anatomy. We need to know where the hand area is because this is where the source of the tracing will begin. And then the leg area is represented here, closer to the midline. The target of the seed ROI here is this target ROI here in the midbrain. Here we have a coronal view demonstrating the centrum semiovale and corona radiata, internal capsule, and the peduncles down here. So blue is for arm fibers, red is for leg fibers. Now, not so well seen here in this DTI study by Kwon et al. So we'll show you a zoomed up picture of this later on. This just demonstrates the location of the arm fibers relative to the leg fibers. So they are more anterior and more medial than the leg fibers down here. Same here. Alright, so not to miss out on our equally important corticobulbar tract, which will control your brainstem motor nuclei to complete the inner homunculus or inner map of ourselves. So the face and head here, the arms here, and the legs here, most posteriorly, which is preserved here in the crus cerebri. So this is very tiny. We're just not just nitpicking here. So relatively small insult or lesion here can cause a paralysis if it's in the peduncles or in the internal capsule posterior limb.